In this tutorial, I'm going to prove that if m and n are consecutive integers, then the sum m plus n is odd. An integer is said to be even if we can write it in the form 2k1, where k1 is an integer, and an integer is said to be odd if we can write it in the form 2k2 plus 1, where the k2 there is an integer. But in this case, we are having two consecutive integers, m and n. But we might have two cases where m is even or m is odd. So we'll look at those two different cases separately. So I'll start by looking at the case where we have m being even. If m is even, then we can write it as m is equals to 2k1, where k1 there is an integer. And we are dealing with consecutive integers. So to move from m to n, which is the next integer, we need to add 1. So to get our n, we just add 1 to the m. So in this case, we would have our n there is 2k1 plus 1. Now to get the m plus n, we use the m and the n that I have just written there. And we would have m plus n is equals to 2k1 plus 2k1 plus 1. 2k1 plus 2k1 gives us a 4k1. So we would have 4k1 plus 1. I can factor a 2 there from the 4k1, and we have 2 times 2k1 plus 1. But what we are having there, 2k1, is just 2 times an integer k1. So if we multiply 2 by an integer k1, we get another integer. And let's call this integer k3. So we would have 2k3 plus 1, where I have substituted there the 2k1 with a k3. And we are saying the 2k1 is an integer just because we are multiplying two integers, 2 and k1. So we have the k3 there is an integer. But if we look at this expression that we are having now and compare it with the form of odd integers there, we see that 2k3 plus 1 is of the form of odd integers. So we can conclude that 2k3 plus 1 there is an odd integer. And if that highlighted part is an odd integer, we would conclude that the m plus n is an odd integer. Now moving on to the second case where we have m being odd. If m is odd, then we can write m as 2k2 plus 1. M and n, they are two consecutive integers. So to get n, we just add 1 to m. So we would have that our n there is 2k2 plus 1 plus 1. And we use that m and n that I've just written to obtain m plus n. And we get that m plus n is equals to 2k2 plus 1 plus 2k2 plus 1 plus 1. We can then simplify that to 4k2 plus 2 plus 1. Where we have that term where we have 4k2 plus 2, I can factor the 2 there, and we have 2 times 2k2 plus 1 plus 1. But that term there, 2 times k2, it gives us an integer, plus 1, it gives us an integer. So I can write that 2k2 plus 1 is k4, and we have 2k4 plus 1. And as I said, 2 times k2 is an integer, plus 1, it gives us another integer. What it will mean is that k4 there is an integer. And if k4 is an integer, if we look at the expression that we have here, 2k4 plus 1, and the form of odd integers there, 2k2 plus 1, we see that 2k4 plus 1 there is of the form of odd integers. So we can say that 2k4 plus 1 there is an odd integer. And if that highlighted part is an odd integer, then we can conclude that m plus n is an odd integer. So in this case, we are having for both cases, when m is even and when m is odd, we are having m plus n is an odd integer. So this was a proof by cases.